Now let's compare a reversible heat and an actual heat. Even though I wrote down the second law of thermodynamics to help you out, but let me just start writing myself. Okay, so please don't worry about this equation. Please delete it. And the second law of thermodynamics can be written as d capital S equals to delta Q. Now, in order to emphasize that it's an actual work, let me put A divided by T and plus delta SG. So if we follow the actual process, then we can write up the second law of thermodynamics as this equation, where, as you know, the delta Sg is actually the entropy generation, which is always greater than 0 or equals to 0. Then what you can write is delta Qa. The amount of actual heat transfer can be written as TdS minus T delta Sg. Or Qa can be written as integration from 1 to 2 T ds minus integration from 1 to 2 T delta Sg. Again, remember that this is entropy generation that is always greater than 0 or at least equals to 0. From the previous discussion, what we learned is that this integration, the first term, is basically same as reversible heat transfer. And now, what you can see from this equation is your actual heat transfer is the amount of reversible heat transfer minus certain positive value, because we have delta Sg, which is positive, and its integration from state 1 to state 2. And let's define the second term as Q loss. So what you can understand from this equation is that the actual amount of heat is always smaller than the reversible amount of heat by the amount of the loss of heat that is not being used for our benefit. So that is how we can compare the reversible heat and an actual heat. Then how about a reversible work and actual work? Now let me change this 2 to 4. Then if you try to write the first law of thermodynamics, okay, let's talk about the closed system first. Then we can write the first law of thermodynamics as that. So that is for reversible process, but actually the first law of thermodynamics does not distinguish reversible process or actual process in terms of its equation form. So same equation can be written for actual process, but in order to emphasize that those are actual process and reversible process, I changed this reversible and A in the subscript. Then what about an open system? Same thing. If you borrow the equation for the steady state, we can write the equation as this, which was derived from the previous page. And this equation is quite the same formulation, even though we choose the process that is an actual. So now everything remains the same, but we have A here as a subscript. Now, let's take a look at both equations for closed system and open system. Now, what is clearly seen in common is that no matter what we write, no matter what process we choose, we might have a different amount of heat transfer and work transfer, whether you choose the actual process or reversible process, but that subtraction between the heat and work still gives us same change of the internal energy. Well, that is for closed system. How about the open system? Same thing. Well, the individual heat and individual work could be different depending on your process, but that difference between the work, heat and work, can be written as the summation of dH, dKe, and dPe, and those right terms should be always the same, for all different processes as you see here. Now, let's equate them together. What you can see is QREV minus QW REV should equal to delta QA minus delta WA. Even for the open system, same thing. Delta Q REV minus delta W REV equals to delta QA minus delta WA. So no matter what system you talk about, still it gives us the same relation. The difference of heat transfer and work transfer for whatever process you choose, either reversible process or actual process, the difference should remain the same. And now that is the equation that I can conclude. Okay. Then let's play a little bit more about this equation. From our previous discussion, the delta Q REV, the reversible heat transfer, can be written as TdS. Then how about delta QA? We also know now is that delta QA can be written as TdS minus T delta SG. Okay. Now let me just write that one to small sg. So remember that this equation is just based on the whole unit mass. Okay, so from this equation, now we see the common term TdS here and common term TdS here. So what you have is minus delta WREV equals to minus T delta SG minus delta WA, or delta WA can be written as delta WREV minus T delta SG. This is the very important equation that we can understand what is the relation between the actual work and then a reversible work. Now again, remember that this delta SG is entropy generation, which is always positive or equals to 0. Now, what you see is always delta WA, the actual work, is smaller than the reversible work. Again, remember that this one is when we think about the work out. Okay. So we can define the second term, that T delta SG, as work loss. Okay, or we call that as lost work. Or we use a new term, that is irreversibility. Okay, and we use symbol I. Okay. Now, when you talk about work out, always your actual work out, okay, let me just try to write it more clearly. Work out is always smaller than the reversible work out. And the difference between these two is this amount can be calculated by T times delta SG. So let me just write it down. So delta work loss can be written as T delta SG. Okay. So the conclusion is here. Why entropy generation is important? Because this entropy generation gives us an information of how much work is actually not being well used compared to the reversible work. So if we can reduce the entropy generation, that means that we can reduce the lost work by the amount of this much, then we can actually get more work out from your process. Okay, so our whole design process should be focused on how we can minimize the entropy generation, because that entropy generation gives us actually the entropy if we just reduce the entropy generation, that means that we also can reduce the lost work. What if we apply the same equation for work input, okay, for compressor, for example? Then this equation can be written as W minus WA in equals to minus delta W reversible in and minus T delta SG. Okay? So what you see is WA in should be equal to delta W reversible in plus T delta SG. Okay? So now the amount of work that we need, okay, in case the work is transferred into your system, should be always greater than the amount of reversible work that is transferred into your system. Okay, and the difference between them is T delta SG. Still, we call that as lost work, but in the case where you can interpret that as the additional work that we have to put into your system in case your system needs work done by the surroundings. So a good example is compressor. So now, if you really want to run a compressor in actual process, actually you need more work than what you would need for the reversible or ideal compressor. Okay, I hope that you clearly understand this, because that is really, really important. Always you need certain amount of work, or you do certain amount of work that is different from the reversible work. And when you actually produce work, always actual work is smaller than the reversible work. And when you do need to put certain work to run your system, the actual work you need to put into your system is always greater than the reversible work that you need to put into the ideal system. And we are going to talk a little more about this difference in the example. Okay, but I really want to emphasize again that now the entropy generation actually tells us the quality of how we can make use of energy for heat and work. Then again, as we discussed, the actual heat, okay, should be smaller than the reversible heat. And more importantly, the actual work out is always smaller than the reversible work out, and actual work in is always greater than the reversible work in.